All right, we're going to recap what we did last week. Last week, in week 6, we looked at two different techniques to control our model. One was regularization and another was validation. Both are different ways of trying to get our test error to look a little bit like what our training error looks like. The first way we do this is by regularization. Regularization is a technique that constrains the model parameters to take on what we would say are reasonable values that can fit the signal of the data better, but not so much the noise. We do this in some ways, for example, using LP norms by creating an overfit penalty. All right, this overfit penalty is going to penalize model parameters that take on very large values, which would exhibit a lot of variance when we looked at different data sets. The second way that we looked at was through validation. Validation means taking a piece of the training data, setting it aside for pseudo test cases, right? We're going to approximate the test error by taking these training data and setting it aside as what we call validation, right? In validation, we actually have the answers so we can approximate how well the system actually does. We can equate that with J-test. This week, we're going to look at a very interesting topic. We're switching gears a little bit and talking about, again, paradigms of machine learning through the lens of reinforcement learning. And reinforcement learning has its own lingual and terminology which we need to understand about policy, rewards, actions, observations, and models. We're going to show in the bottom half of this lecture what the Markov decision process framework looks like, which nicely encapsulates the idea of reinforcement learning. In the post part of the lecture, we'll be looking at the Bellman equations and how they exhibit a recursive form to understand reinforcement learning and coupling this idea of future rewards and state values. Finally, we're going to look at two different algorithms, one for planning when we actually know the Markov decision process incomplete. That's called value iteration. And a second problem, which is more akin to learning. Okay, learning meaning that we have to explore at the state space and the reward function in order to get a good approximation of the actual optimal route to get an answer to our question of how to behave in a decision process. And that is called Q-learning. So now, let's get started.